Hello, I am Dr. D.S. Kushan. Today I am sharing research on nanoscale friction modifier coatings for railway applications, specifically focusing on solid lubrication mechanisms. This builds on our published work on application methodology and surrogate models and extends to multi-component solid lubricant coatings using a novel deposition technique. The rail wheel interface faces extreme tribological challenges. During acceleration, high shear forces drive the wheel forward. During braking, severe retarding forces and thermal stresses dominate. During turns, lateral forces create additional wear and friction variability that's difficult to control. Traditional liquid lubricants struggle here. They wash away, degrade under extreme pressures, and can't provide consistent friction across all three regimes. Solid lubrication offers a fundamentally different approach. We deposit engineered nanoscale coatings directly on rail and wheel surfaces. These coatings remain in place, respond intelligently to operating conditions, and can be optimized for railway specific demands. Our published work had four objectives. First, develop a nanoscale solid lubricant coating system for Indian Railway service rail steel. Second, establish a reproducible deposition methodology for uniform stable coatings. Third, characterize friction and wear across realistic operating loads, speeds, and temperatures. And fourth, critically build surrogate models that predict friction behavior without running hundreds of tests. These models enable rapid optimization for different railway networks and train types. We tested on actual IRS rail steel using ball-on-disc tribometry to simulate rolling sliding contact. We deposited solid lubricant coatings with carefully controlled thickness and coverage, then measured friction across a systematic matrix, varying loads representing different train masses and varying sliding speeds. We used scanning electron microscopy and profilometry to understand coating structure and its relationship to tribological performance. This mechanistic understanding is essential. It tells us why the coatings work, not just that they do. Our key findings focused entirely on solid lubrication mechanisms. First, the solid lubricant coatings reduce steady state friction by 30 to 45% compared to uncoated rail steel, significant for energy efficiency. Second, and this is crucial for solid lubrication, the friction is stable across load, speed, and temperature variations. Unlike liquid lubricants that fail under extreme pressures, solid lubricants maintain consistent performance. This is because the solid lubricant, typically a layered material like MOS2 or graphite at the nanoscale, provides intrinsic low friction through weak interlayer shear. Third, post-test wear analysis revealed the protective mechanism. The solid lubricant coating transfers a protective film to the counterface, reducing direct metal-on-metal contact and subsurface damage. This is the fundamental advantage of solid lubrication. It sacrifices a tiny amount of coating to protect the underlying rail steel from rolling contact fatigue. This solid lubrication approach is especially suited to railways because it's durable, predictable, and doesn't depend on liquid film continuity. We trained surrogate models on experimental data to predict friction from operating parameters. For railways, this is transformative. A network can now ask, for this specific train mass, speed, and track temperature, what will my solid lubricant coating deliver? And get instant predictions. These models enable sensitivity analysis, identifying which parameters most affect solid lubricant performance, and optimization of coating design for specific railway applications. The framework extends to different solid lubricant chemistries and rail grades globally. Our published work proved solid lubricant coatings work. Now we are advancing to multi-component solid lubricant architectures. We realized that acceleration, braking, and turning demand different solid lubricant characteristics. Multi-component designs let us tailor different functional zones, one optimized for high traction during acceleration, another for controlled braking, another for lateral force management. We developed a novel deposition technique enabling unprecedented control over solid lubricant layer architecture, composition, and nanostructure. Multi-component solid lubricant coatings combine different nanoscale constituents. During acceleration, you need solid lubricants promoting load transfer and traction. During braking, you need ones providing reliable, controlled friction. During turns, you need to manage lateral forces without excessive slip. By engineering multiple solid lubricant phases within a single coating, we achieve targeted control across all regimes. The design space expands dramatically, but our surrogate models make exploring it computationally feasible. Our novel deposition technique enables precise control over solid lubricant layer thickness to nanometer accuracy, composition gradients, and nanostructure. We can engineer layered solid lubricant architectures, each layer optimized for specific tribological functions that support extreme rail wheel contact pressures while maintaining low friction. It's compatible with industrial rail production, allowing deployment on real railways at scale. This research has generated 4 significant conference presentations, all focused on solid lubrication and railway applications. ICFP 2025 in Tirupati on water-based solid friction modifiers. ICTA-SEM 2025 at IIT Kharagpur on morphological effects of solid lubricants versus binders. And parametric studies of solid lubrication on IRS rail steel. INECOM 2025 in Hyderabad on mineral versus oxide solid lubricant systems. This work bridges on nano-scale solid lubricant design with real Indian Railway deployment. Thank you. I am happy to discuss the solid lubrication mechanisms, surrogate model, and railway specific applications.